Consider a situation. Let us say that you have gone to a shop in order to buy cold drinks, and the shopkeeper gives you the bottle along with a straw. Now, it is common knowledge, and you must be knowing that when the straw is simply placed inside the liquid, that is the cold drinks, no amount of cold drinks or liquid moves into the straw. That is, when I simply, or when the shopkeeper simply places the straw inside the bottle of cold drinks, nothing happens, right? The liquid is not pushed into the straw. However, the moment you bring your mouth to the straw and start sucking, you will find that liquid is pushed into the straw, which is why you're able to drink the moment you start sucking from the other end of the straw. Now, why is it so? Why is it that before you started sucking, no amount of liquid was moving in, but after you started sucking, this liquid that is present in the bottle started moving up and you were able to drink it? Let us explain this scientifically and see how this is happening. Now, in order to do so, we must study about an important concept which is related to the atmosphere of the Earth. Now, what is the atmosphere of the Earth? The big envelope of air that is present all around the Earth is known as the atmosphere. Now, as you can see in this picture, this is the Earth and this is the surface of the Earth. Now, all around the surface of the Earth, there happens to be a huge envelope of air. This envelope of air extends for a certain height above the surface of the Earth. This envelope of air is also known as the atmosphere. So now consider the fact that atmosphere is made up of a lot of molecules because it is primarily gas, and obviously it will have molecules, and since it is present to a certain height above the surface of the Earth, all around the Earth, it will be made up of a lot of molecules, billions and billions of molecules. Similarly, it is due to this reason that the atmosphere will have a certain amount of weight, because these molecules will be attracted by the gravity of the Earth and they will be exerting their weight in this direction on the surface of the Earth. So consider billions and billions of molecules all exerting their weight simultaneously on the surface of the Earth. So obviously, this atmosphere in its entirety will exert its weight on the Earth. So we can say that the atmosphere exerts thrust. Why? Because since gravity always acts towards the center of the Earth, and since these molecules are present all around, we can say that the force they are exerting on the surface of the Earth is perpendicular. In other words, the atmosphere all around the Earth exerts a certain amount of thrust on the surface of the Earth. Now we arrive at a very important term which is known as atmospheric pressure. What is atmospheric pressure? Atmospheric pressure is the thrust exerted on unit area of the Earth's surface. The thrust exerted on unit area of the Earth's surface due to the column of air or the envelope of air surrounding the Earth is known as atmospheric pressure on the surface of the Earth. So atmospheric pressure is nothing but the weight of the gas molecules all around the Earth exerted per unit area of Earth's surface. Now atmospheric pressure acts not on selected objects. It acts uniformly on all objects that are on the Earth. Just like atmospheric pressure will be acting on the book that you read from, it will also act on the table at which you study. And in a similar manner, it also acts on your house where you stay. So thus we can say that atmospheric pressure is exerted on every object that is present on the Earth as well as on the Earth itself. So now consider what was happening in the case of the Coke bottle and the straw. Initially, when the bottle simply had the straw put into it, no amount of liquid or cold drinks was getting inside the straw. Why? Because initially the atmospheric pressure was acting both inside the straw as well as on the surface of the liquid in the Coke bottle. So since atmospheric pressure was acting on the liquid as well as the straw, there was no pressure difference in between the liquid and the inside of the straw. And it is due to this reason that liquid did not move into the straw. However, the moment you suck from the other end of the straw, a partial vacuum is created inside the straw, due to which the pressure inside the straw becomes nearly equal to zero. So what happens? Outside, on the surface of the liquid, atmospheric pressure is still acting. Whereas inside the straw, the pressure has suddenly dropped because you have sucked out air. So as a result, pressure inside the straw decreases. And we have studied that fluids, liquids and gases alike, flow from a region of high pressure to a region of low pressure. So in this case, the cold drinks will flow from a region of high pressure, that is the bottle, to a region of low pressure, that is inside the straw. So it is due to this reason that this liquid moves inside the straw. So since liquid is at high pressure as compared to the inside of the straw, liquid rushes into the straw the moment you suck at the other end of the straw. Because fluids, and liquid is also a fluid, flows from high pressure region to low pressure region. Now I have a question for you. The question is, why does a fountain pen leak if taken to a higher altitude? I'm sure you must have used a fountain pen at some point in your life. Now, normally, under normal working conditions of the fountain pen, you will find that it functions properly and ink does not leak. However, if you take the same fountain pen to a higher altitude, let's say a hill station, you will find that it starts to leak. Why is it so? Let us find out the reason behind the leaking of the fountain pen and explain it scientifically. Now again we consider the atmosphere, that is the big envelope of air that is present around the earth. And now we are going to zoom into a particular part of the atmosphere. This part can be anywhere in the atmosphere. Just for the sake of convenience, I am zooming into one part. So let us zoom into this part and find out its composition. So after zooming into that part, I find that the air molecules are distributed in the following manner. Absolutely at the surface of the earth, that is the purple region, the air molecules are at its densest, at their densest. They are very closely packed and they are nearby one another. So we can say that the density of air near the surface of the earth is quite high. But as we move up from the surface of the earth, that is, as we go from A to B, then B to C, and even C to D, we find that the density decreases. Or in other words, the arrangement of the air molecules becomes more sparse. So we can say that as we are going up or moving up from the surface of the earth, the height from the surface of the earth is increasing. Or in other words, our altitude is increasing. Now, as you saw in the previous picture, the moment altitude increases or height from the surface of the earth increases, the number of molecules become less. Because at the surface of the earth, the molecules of air are densely packed, whereas as we move upwards, the molecules are sparsely packed. Thus, the moment the altitude increases, the number of molecules decreases. So at the top, at a very high altitude, the number of molecules present is much less than the number of molecules at the surface of the earth. What does this imply? This implies that weight of air above decreases. So if we consider a particular area, that area, the same area at the surface of the earth, as well as at a point very high above from the surface of the earth. At the surface of the earth, more number of molecules are exerting their weight on that area. So we can say that the force per area is more. However, if we consider the point high above, we find that the number of molecules on the same area exerting their weight is less. So the force per unit area is less. Now since this force by the molecules is being exerted perpendicularly, we can say that thrust per unit area at the surface of the earth is more, and the thrust per unit area at an altitude high above the earth is less. So what does this imply? This implies that as we move up, the atmospheric pressure decreases, or in other words, the pressure exerted by the molecules of air decreases as we move up from the surface of the earth. So thus, since region A is closest to the surface of the earth, we can say that the atmospheric pressure will be maximum at A, because the height of A is minimum from the surface of the earth. In a similar manner, atmospheric pressure will be minimum at D. Why? Because the height of D is maximum from the surface of the earth. So at A, as we found, the molecules are quite densely packed of air, and at D, the molecules of air are much less densely packed. So we can say that atmospheric pressure, while maximum at A, is minimum at D. So we saw that as we are moving up from the surface of the earth, atmospheric pressure is decreasing. So now with the help of this, let us try to explain what was happening in the case of the ink pen or the fountain pen. Now at normal altitude, if you consider the pen, it has a cylinder inside it which contains ink. So at normal altitude, this fountain pen that has a cylinder inside containing ink will not leak. Why? Because the ink inside the cylinder is exerting a pressure on the inner walls of the cylinder, but the ink is not coming out of the cylinder. Why? Because there is an atmospheric pressure on the cylinder which is equivalent. The atmospheric pressure is equivalent or equal to the pressure inside the cylinder due to ink. So if this is the cylinder and ink is everywhere inside the cylinder, the pressure that the ink is applying is on the inner walls of the cylinder, and atmospheric pressure is acting on the outer walls of the cylinder, and these two cancel out one another. So it is counterbalanced, and it is due to this reason that the net pressure on the pen is zero, and as a result, the fountain pen does not leak when it is kept at normal altitude. Now what happens when we go to a higher altitude? As we have seen, the more we move up from the surface of the earth, the atmospheric pressure decreases and becomes less and less. So when we are going up, the pressure exerted by the ink inside the cylinder will not change. Why? Because the cylinder and the ink quantity remains the same. However, the atmospheric pressure is decreasing. So as a result, what is happening? The pressure inside the cylinder is greater than the atmospheric pressure that is outside being exerted on the cylinder. So we have studied that liquids always flow from a region of high pressure to a region of low pressure. So if we have a cylinder inside which there is ink, and if the pressure exerted by the ink on the inner walls of the cylinder remains the same, but the atmospheric pressure decreases, we will find that these two pressures are no longer counterbalancing one another. Instead, the pressure from the inside is increasing. And since fluids flow from a region of high pressure to low pressure, ink from the cylinder starts to come out. And as a result, when the pen is taken to a higher altitude, it starts to leak. Now we have studied all about how the atmosphere is exerting a pressure on us. Now, how much do you think is the atmospheric pressure? When I am saying that there is atmospheric pressure on us, the term might seem quite abstract to you, and you might wonder that how big or how large this atmospheric pressure is. Or speaking in scientific terms, what is the magnitude of atmospheric pressure? The magnitude of atmospheric pressure or air pressure is 101,000 325 pascals. This quantity is also known as 1 atmospheric pressure. So 1 atmospheric pressure is equal to 101,325 pascals. As I have previously told you, pascals is the SI unit for pressure. Now, I have told you that the atmospheric pressure on us is this much. Now, again, this quantity might not make sense to you. You might wonder that how big is this 101,325 Pascal? How can I relate it to something that also applies pressure? In other words, how heavy is 101,325 Pascals? An atmospheric pressure of 101,325 pascals is roughly equivalent to carrying an object of 100 kgs on our heads. So imagine that you have a 100 kg object on your head. That much is the atmospheric pressure that is acting on you. Now you might be wondering that if such a heavy pressure is acting on our heads all the times, why is it not affecting us? As a matter of fact, our entire body is surrounded by air, and it is not just our head, but atmospheric pressure is acting on every part of our body. So if such a heavy pressure that is equivalent to 100 kg mass on us is acting on us at all times, how come it is not affecting us in any way at all? If atmospheric pressure acts on each and every part of our body, why are we human beings or any other living being for that matter not getting crushed? So consider this picture. Over here you will find that these black arrows represent atmospheric pressure, and atmospheric pressure is acting on every part of the human body. But despite this, the human body is not getting crushed. Why? This is because blood is also flowing inside the human body and in the living body and in the body of any living being. So as a result, what happens is this blood flowing through the human body exerts a certain amount of pressure from the inside of the human body. In other words, when the heart is beating and blood is traveling through the blood vessels, it exerts a certain amount of force on the inner walls of these vessels. And this blood vessel and this blood that is flowing through the blood vessels exerts a pressure that counterbalances the atmospheric pressure. So we can say that pressure exerted by the red arrows depicting blood and black arrows depicting atmospheric pressure are equivalent. So it is due to this reason that we are not getting crushed by atmospheric pressure, because the net effect of pressure on our body is zero. Blood pressure is cancelling out atmospheric pressure and we are not getting crushed. Now let me tell you a fun fact. You must have seen in movies or seen pictures on the net or newspaper that when an astronaut is going into outer space, let's say on the moon or anywhere else in outer space, when he has to leave the rocket or the space shuttle where he was traveling in, he or she will have to wear a specialized suit. That is the suit which astronauts wear. So these special suits that astronauts wear, what is the significance of these suits? Can astronauts do without this suit, or is the suit absolutely necessary? And if so, why is it necessary? Now we have seen that when anybody is in space, he or she or any object will experience no pressure. Why? Because in space there is no atmosphere. In space there is no atmosphere, which means there are no particles or no molecules of atmosphere or air, and as a result the atmospheric pressure is zero. There is no atmosphere to exert its weight or its pressure on our bodies outside in outer space. So as a result, what happens? Pressure outside the body is zero because there is no atmosphere. So there is no pressure being applied outside on our body. However, blood continues to flow inside our body and it goes on exerting a pressure from inside the body. So as a result, what happens? Pressure inside the body equals the pressure of blood. but there is no pressure from outside to counterbalance this pressure. The human skin or the skin of any living being is quite elastic. So when the pressure is not balanced from inside, what happens is the human skin starts to expand because of the pressure being exerted by blood while flowing in the vessels. So the human body goes on expanding, and a time will come when it reaches its limit and the body expands more and more and bursts off. Obviously, an astronaut going into outer space would not want such a condition to endanger his life. And it is due to this reason, to prevent this expansion of the human body, that the astronauts wear these special suits. Now, these special suits are special because they are pressurized from the inside. These suits are pressurized suits. So, to counterbalance the pressure being exerted by our blood flowing in the blood vessels, these suits exert an equivalent amount of pressure on our bodies. So, it is due to this reason that the blood pressure is counterbalanced by the pressure exerted by the suit. And it is due to this reason that the net effect of pressure on our body is zero. There is no net pressure acting on our body, and thus the astronauts remain safe with the help of these suits even in outer space.